So I just discussed that thing. So we shall now exploit these features to filter out, separate arrays completely. So here is the basic principle of that. So this is the basic principle of Nicol prism, invented by William Nicol. Now we all know, again by reference to our school geometrical optics, that a prism is a material. A prism is a device, very simple device, by which we can separate different constituent colors of light. So here also we are trying to do something, separate two light rays, but not so much with regard to their colors, but with regard as it is with regard to their polarization state. So here let us now try to see. So a Nicol prism is made up of calcite material. So here is uh, the basic structure of calcite crystal. Now what is done is that uh, two such it's broken, it's cleaved along the obtuse angles and formed a structure like this. And then the two parts are joined by an adhesive known as Canada balsam. Now, the width of the the length of the prism is 3 times the width of the prism. And there's a slight more difficulty over here. This angle naturally is 72 degrees, the acute angle. Here it is chiseled down to 68 degrees. It's made even more acute. So that's not a very easy thing to do, because it requires some fine sharpening skill and chiseling skill, whatever it is. Now let us look at the basic principle of this arrangement. uh, like I told you, extraordinary rays have a different refractive index compared to ordinary rays. So for this material, ordinary rays have the refractive index of 1.66, whereas extraordinary rays have the refractive index of 1.49. So clearly, as you can see, extraordinary rays, noting that refractive index is equal to C as in the speed of light in vacuum, divided by the speed of light in a medium. If the extraordinary rays have a lower refractive index compared to ordinary rays, it means that the speed of extraordinary rays in this particular material is higher than that of ordinary rays. So that is what it is. But this balsam is a transparent material, some sort of a glue. That is, it's basically this whole structure, except that it has been broken along this obtuse angles and then joined with the help of this glue. What is the meaning of doing this complicated thing? It is just this, that the balsam has got an intermediate refractive index between the refractive indices of ordinary rays and extraordinary rays. Let us therefore now see what happens. So, if light goes from an optically denser material to an optically rarer medium, optically denser medium to optically rarer medium, then light undergoes this phenomenon known as total internal reflection. So, if you note that for ordinary rays, the refractive index is greater than the refractive index of this balsam material, which means that it is possible, if we can adjust our initial angle of incidence to a certain critical value, to make the ordinary rays undergo total internal reflection, which is actually refraction, but total internal reflection at the balsam calcite interface. Whereas for extraordinary rays, nothing of the kind will happen, because extraordinary rays have a refractive index that is lower than that of the the balsam material. As a result, it will just drill through. And so here, the E rays will transmit through and come from this side, whereas the O rays, the ordinary rays, will be swerved and totally internally reflected for large angles of incidence. So the critical angle is 69 degrees. So for large angles of incidence, the O rays will come to this side. So what have we done here? Let's go back to a previous diagram. In the previous diagram here, both the rays were coming out from out of the same face. So you still couldn't, although each will have its own separated state of polarization, but the rays are still in the going in the same direction. But now with the help of a Nicol prism, you have separated their directions completely. It is as if one, I mean, they are going in almost in mutually perpendicular directions. So you can thereafter capture the E rays on this side and the O rays here on this side. So that is what has been achieved by the by this Nicol prism. So O rays will and the E rays thereafter could be captured in your spectrograph or whatever, and then you will have complete state of polarization using the same original incident beam of light, and then split into two components, sorry, into two polarized states. Well, components is also not a very wrong thing to say, because this plane, the extraordinary rays will be oscillating on the plane of the paper, whereas the ordinary rays will be oscillating perpendicular to the plane of this paper. So in that sense, separated components as well. So now what we shall do is look at certain behaviors and certain features of calcite and quartz. Now we have talked about calcite, where the very mention of the fact that E rays have a lower refractive index than O rays means that E rays travel faster than O rays. So here we look at some sort of behavior like that. I mean, this is a schematic diagram. First, let's just imagine a situation uh, far removed from optics as it is. Imagine still water on a lake, right? And now from above, let's say from a drone or whatever, you have dropped a stone on the water surface. From the point of impact of the stone on the water surface, surface waves will start rippling out, and the wave front viewed from above will be perfectly circular. Why is it circular? Because along all directions, the wave front, the waves will be traveling at the same speed. There will be no greater direction along one axis or along another. So if you decompose the ripples, the circular ripples, into two directions, x and y, the wave front will form a part of a circle on this xy coordinate axis system. The equation of a coordinate I mean, it's x squared plus y squared is equal to radius squared. So with successive time, the radius of course is a function of t, because the waves are spreading out, they are not fixed. So that is what it is. But what happens if the waves were to, strange kind of waves, let's say we are imagining some sort of liquid material in which waves travel with different speeds along different direction. Let us say along the x-axis, it is traveling at a greater speed compared to what it does along the than what it does along the y-axis. So then the wave front will be stretched along the x-axis as compared to the y-axis, and as a result the wave front will not be circular, it will become elliptical. So something similar happens in the case of quartz crystal. Let us now try to understand this thing. So here we are talking about birefringent crystal, double refracting crystal with a single axis. Let's now just see, here's a point P. Let us say that that point P is a source of waves. It could be a secondary source, it could be a primary source, whatever. We are not worrying too much about that. We are just worrying about the simple geometrical construct of what happens. Uh, Remember, these crystals are anisotropic crystals, which means that the same feature will not be seen in every direction. So here is something like that happening. So the ordinary waves or the ordinary rays will behave ordinarily. That is to say that they will travel along different directions with the same speed. So starting at a particular point in time, the wave front of the ordinary rays will be a circular, this red circle, spherical, or projected in 3 dimension. It will have a spherical wavefront of the ordinary rays. And but the extraordinary waves or the extraordinary rays will show this strange behavior, that along one direction it will travel faster than the ordinary rays, let us say along the horizontal direction, as has been drawn over here, the major axis of the ellipse actually. So along the major axis, it will form an elliptical front, of course, because it is traveling along the two directions with two different speeds. So along the axis of greatest disparity, it will travel far faster than the ordinary rays, and therefore there will be a large gap between the two. Whereas along the other direction, it will travel with the same speed of the ordinary rays. Therefore, the wave fronts will touch over here. So elliptical wavefront, when you rotate this thing in 3 dimension, you will have a sphere for this red circle and an ellipsoid for this green circle. So ellipsoidal wavefront of extraordinary rays and spherical wavefront of ordinary rays. And this is the minor axis. So you can see the speeds are the same along the minor axis of this ellipse, but the speeds have largest difference or greatest disparity along the major axis, and along other directions you will have intermediate differences, and then the difference will be zero along the minor axis. So extraordinary rays will have higher velocities than ordinary rays, except along the optic axis. This is the optic axis. So along the optic axis there will be symmetric behavior, so they will show the same kind of behavior. So this is known as a negative crystal. I will come to the definition of positive and negative in due course. So this is known as a negative crystal. Let us now see what happens to a different kind of situation where the ordinary rays are traveling faster than the extraordinary rays. So here's that sort of a situation. Here it is that this is the ellipse. The ordinary rays wavefront has enveloped the extraordinary ray wavefront. Let us now try to understand here. Along the major axis of the ellipse, remember the faster velocity will always be along the major axis. In the previous diagram, the faster velocity for the extraordinary ray was along the major axis, and the slower velocity was along the minor axis. Now the velocity of the extraordinary ray along the slower axis is also the velocity of the ordinary rays. So that is the reason why in this diagram the ellipse has enveloped the circle. But it is the other way around in the next diagram. The faster velocity for the extraordinary ray is of course along the major axis, and the slower velocity is along the minor axis, but the faster velocity is now coinciding the velocity of the ordinary rays, which are forming this spherical, or rather the circle, which is enveloping the ellipse over here. And so the axis of disparity is now along the minor axis of the ellipse. So in the previous case, the axis of disparity was along the major axis, and here the axis of disparity is along the this minor axis of the ellipse. The ellipse is represented by this green track, and of course when you rotate it, this will form an ellipsoid, and the outer circle will form an enveloping sphere. So spherical wavefront of O rays and ellipsoidal wavefront of E rays. So the major axis, this is where you will have the cross section, the ellipse, major axis of the ellipse. We have just drawn the cross section of this. The optic axis is along the major axis over here. So E rays have lower velocity than O rays, except along the optic axis. So this is known as what we call a positive crystal. So let us now try to understand the concept of positivity and negativity. Let us see. Refractive indices and bright refringence. So in negative crystals, well, the definition is that for extraordinary rays, the refractive index is c, which is the speed of light in vacuum divided by the maximum velocity of E waves. And in positive crystals, it is C divided by the minimum velocity of E waves. So here, let us go back. In this thing is the refractive index is defined by the speed of light in vacuum divided by the speed with which the E rays are moving along the major axis of this ellipse, this engulfing thing. You can see that the speed of O rays is less than the speed of E rays along this major axis, which means that the refractive index of O rays will be greater than the refractive index of E rays, because refractive index is inversely proportional to the speed with which light is propagating in a medium, right? So E rays have greater speed, therefore its refractive index will be less. O rays have the lower speed, and refractive index will be more. So in positive crystals, it is the other way around. In both cases, the ordinary refractive index will be C divided by the velocity of the ordinary waves, okay, or the ordinary rays. So by refringence, this quantity is defined as refractive index of the ordinary rays, I'm sorry, extraordinary rays minus the refractive index of the ordinary rays. So in negative crystals, such as calcite, note that it is for negative crystals, it is defined by C divided by the maximum velocity, right? You are to define not along the velocity in the direction where both have the same values. It's always the velocity of the extraordinary rays that will be chosen to define the refractive index will be the along the direction of the maximum disparity, or the axis of the maximum disparity. For negative crystals, it will be this velocity, the minimum velocity. At other points on this wavefront, the velocity will have higher values. So for negative crystals, it is this, for positive crystals, it is this velocity. For negative crystals, it is this velocity that you take. So when you do that, negative crystals will give you the birefringence value to be negative. Ne minus No. Ne in a negative crystal will be less, because the velocity in a negative crystal will be higher or the speed of propagation in a negative crystal will be higher for E rays than for O rays. And it is the other way around for positive crystals such as quartz. Here, E rays have a lower speed than O rays. Therefore, the refractive index of E rays will be higher than the refractive index for O rays. So that is the idea of negative and positive crystals. Calcite is a negative crystal material. Quartz is a positive crystal material. Inside quartz, you will see this kind of a general schematic representation, and inside, with pertaining to calcite, you will see this kind of a schematic representation. So these ideas we can now apply to wave fronts. Let us now see. This is the idea of Christian Huygens. He established the concept of light being a wave. Incidentally, just to delve a little into history, Isaac Newton thought that light was just a stream of particles, and he gave this physical representation of light the corpuscular form. So light was a stream of very small particles. He called them corpuscular particles, and the corpuscles. So that established the corpuscular theory of light. But it was Christian Huygens who showed that light was actually a wave. So the light being a stream of particles, because Newton had studied light as a geometrical feature, a phenomenon, ray paths joining straight lines this way, that way. So that is so, and these rays are defined by stream of particles moving in succession. That was the Newtonian picture of light. But Huygens brought in the idea of wave fronts, or wave picture of light. And just to delve into a little bit of interesting history, it was Albert Einstein who eventually, in a certain way, not exactly like Newton's, revived Newton's particle stream picture of light through his photons in photoelectric effect. In photoelectricity, light becomes a stream of particles, just like Newton had imagined it to be. So, in a way, Einstein revived that sort of a Newtonian picture of a stream of corpuscles. But okay, that's just broadly speaking. There are so many other details to be considered. So light in that sense is both a wave and a stream of particles. As waves, there are three phenomena: interference, diffraction, and polarization, as we are talking about now. But as particles, light also submits itself to three phenomena: black body radiation of Max Planck, Einstein's photoelectricity, and then Compton effect, where Compton married both special theory of relativity and Einstein's photoelectricity to show the and give the complete theory of Compton scattering, and experimentally verified also. But here we are talking about wavefront formalism of light, whose father was Christian Huygens. We are talking using a negative crystal such as calcite. Okay, let us now recall our little discussion over here. This is what a negative crystal looks like. Remember, in the case of a negative crystal, the extraordinary rays travel faster than ordinary rays. Therefore, the ellipse of a negative crystal will always envelop the circle. Ellipse of the extraordinary rays in a negative crystal will always envelop the circle of the ordinary rays of the same crystal. So that is the picture. Incidentally, in a positive crystal, it will be the other way around, but we shall work with a negative crystal over here. So let us now try to see. Light is falling. This is a crystal material. This horizontal line is the interface. Above that is air. Below that is the crystal material. Light is incident on this crystal material at normal incidence. Right. Okay. So the ordinary rays will show no deviation. They will just, from this point, they will travel straight on and form what is known as a circular wavefront. These are the points of secondary wavefront. At this point P, this point P.
Sorry to interrupt you. There is one question from a participant. Can we take questions in between also?
Yes. Please, please.
So someone
Right.
is asking when light is particle, when is the light particle and when it is acting like wave?
Well, the answer is very simple. When light goes to very high frequencies, you can treat light as more. See, it's wave particle duality. First of all, let us be a little clear on that thing. Wave particle duality. So every time, at every point of time, wave behavior and particle behavior will be there. But when light goes to very low frequencies, then low frequencies mean long wavelength, then the wave behavior will be more apparent than the particle behavior. Whereas when light goes to very high frequencies, then the particle behavior of light will become more appreciable. So as a result, I'll give you a simple example. All of light is the entire, when I say light, I mean actually the full range of the electromagnetic spectrum, right? uh, Radio waves, microwaves, these are not harmful for you. Your mobile phone is using radio waves. Your microwave in the kitchen is using microwaves. You are working with these things, standing close to them. They don't they are not supposed to cause you any physical harm. They are electromagnetic waves. They travel with the speed of light, c. But on the other hand, if you look at X rays or gamma rays, prolonged exposure to these rays is considered harmful. Why are they considered harmful? For the simple reason that their wavelength has become very small now. And as such, they have become more particle like. When you have large wavelength, things are diffused and things appear more like waves. But when you have very small wavelength, then things become more particle bullet like, right? And so instead of a soft wave of like when you talk with your mobile phone, radio waves are passing through your head. When you're cooking, radio waves microwaves are passing through your body. So they're like soft waves wafting through your body. But when you have gamma rays, instead of waves, they are now becoming photon bullets. And these bullets, as they travel through your body, they cause a lot of DNA damage, tissue damage. So it all depends. But it doesn't mean that the wave behavior is not there. But it is just that to understand that wave behavior, when you go to very high frequencies, you will need systems which will be able to capture the smallness of those waves, right? Otherwise you can treat them as particles. Whereas for large wavelength like microwaves and radio waves, they can go up to centimeter, meter, that sort of wavelength, right? So they will not cause you any bodily harm. So it all depends on at what wavelength. Long wavelength, more wave like. Short wavelength, more particle like. That is what it is. But more, I'm not saying 100% particle like or 100% wave like. Very large wave like behavior at long wavelength, and very large particle like behavior at short wavelength, but the duality will always be there. Neither of the phenomena will be eradicated completely or 100%. I hope that answers the question. But when Christian Huygens established his wavefront formalism, there was no concept of the full electromagnetic spectrum or the idea of a photon. Well, I mean, Newton had established corpuscles and talked about corpuscles and all that, but there was no photon and gamma rays and bullet like things and all of that thing. So light is a wave for our purposes. We do see light like wave, but light can also be particle at times. Incidentally, photoelectricity that Einstein established or theorized about, photoelectricity is not visible with photoelectricity can't happen with your radio wave or microwave. Photoelectricity can happen only with ultraviolet. So you can immediately see it goes beyond light, right? Or light of, let's say, blue color of that, high frequency light at the high frequency end. Better ultraviolet. So that is what it is. So I hope that answers the question. But so Christian Huygens
Yes,
is.
I mean, it answers the question. There is one more question. Can we take another question?
Yes, 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 yes.
So, the question is, how do Maxwell's boundary conditions lead to the generation of two refracted rays at the surface of a birefringent medium?
How do Maxwell's, oh, that's a pretty difficult mathematical question. So, how do Maxwell's boundary, I
Boundary
mean,
condition lead to the generation of two refracted rays at the surface of birefringent medium.
um, well, that I don't think I can answer too easily because you have to go to the full working behavior. I mean, well, maybe I'll just look into the literature and perhaps come back to you later about this.
Sure.
We have classes for 2 more days, right? If I do come up with an answer, otherwise I shall have to offer my regrets. But yeah, well, that's a valid question actually, because of course, I mean, the extraordinary ray is also an electromagnetic wave, and accordingly, it should be a part of it. It's not going to rise. It may be extraordinary in a simple optical, commonplace optical sense, but it's not so extraordinary that it will rise above Maxwell. So probably that's a very valid question. I'll look into that. Right? Okay.
Uh,
Sure.
there, there is uh, there is one more question.
Yes. Yes.
Why
Please.
why does the ordinary ray obey Snell's law strictly, but the extraordinary rays does not in birefringent crystals?
So probably the answer will be connected to the second question. I think because
The
we have.
previous question.
Yeah, because
Okay.
I mean, basic physics, you go down to Maxwell, then you do all the mathematical workout, and then you will be able to separate the feature of the birefringent material from an ordinary material. So why does it do so? The physics is what am I discussing? What I'm discussing now is a simple phenomenology of it, right? So I think the full mathematical theory should ultimately come from Maxwell. So probably that's the answer that I can offer now, right?
All right.
Okay,
Okay.
okay. So anyway, so here you have a refracting edge. As you can see that this is the point of incidence. This is the original ray path, and this dotted line slightly inclined to the right is the optic axis. This optic axis is the line along which both the ordinary ray and the extraordinary ray will have the same speed, right? So, but anywhere away from that, they will have different speeds, and this horizontal line that I have drawn over here is the wavefront of the red waves, that is to say the ordinary waves, and this lower line is the wavefront of the extraordinary waves. As you can see, starting from this point, both of them have progressed, but the extraordinary wave fronts have already gone ahead of the ordinary wave front. It's only along the optic axis that they travel at the same speed. So what we shall discuss are three cases. Optic axis, this dotted line is perpendicular to the refracting edge, right? Meaning you bring it down and coincide it with this vertical line. So, but is perpendicular to the refracting edge, but on the plane of incidence, meaning you rotate this dotted line and coincide it with this vertical dotted line. Okay. Second is optic axis parallel to the refracting edge, meaning this is the refracting edge. In the previous case, it was perpendicular. Here it is parallel to the refracting edge, but on the plane of incidence, meaning that you take it up and coincide it with this thing. But in both cases, this dotted inclined line will continue to be on this plane of incidence. And in the third case, optic axis is perpendicular to both the refracting edge and the plane of incidence, which means that you have lifted it out of the plane of the paper. It is perpendicular to both this line as well as this line, and so it is pointing towards you. In these three cases, how will you see the geometrical layout of these wave fronts? Let us see. Optic axis perpendicular to refracting edge but on the plane of incidence. Very simple. You pull it down here, what you will get is this diagram. Case 1. It has earlier, this is the optic axis, this is the diagram, this is the path along which the original wave was propagating. The optic axis is also coinciding with that, and as a result, this is what it will look like. So this is the major axis. This is the simple thing that you can imagine. Okay, so that is the first case. The second case is this. The second case is that you lift this thing to the right, and as a result, this point will come to this line, and similarly there will be another point that will come to this line, and here you will have observed the largest gap between these two lines. Case 2. This is the refracting edge. This is the minor axis. The optic axis is now along this line, and this is the major axis along which the extraordinary ray is staring ahead of the ordinary ray. So this is the second case. This is just simple geometrical layout that we are having. And case 3, optic axis coming out perpendicular to the from the point P. Let us now see what you will look at. So you are looking at this axis head on from below as it has been lifted and brought up to this, perpendicular to this, perpendicular to this, and pointing towards you. You are looking at this whole thing from the bottom. What you will see is the propagation of two circles rippling out, as let's say if you're looking at the earth from above the north pole or the south pole, what you will see will be like those lines of latitude going rippling out like that in circular path. So there it is. You will have the ordinary rays, you'll have the extraordinary rays. You're looking at it along the optic axis. So about the optic axis, you will have perfectly symmetric behavior. There will be no asymmetry between the ordinary and the extraordinary rays. The only only difference will be that the ordinary rays will be falling behind the extraordinary rays. If we were to have imagined the same scenario looking along the optic axis for a positive crystal, this is a negative crystal, of course, where the extraordinary rays travel faster than ordinary rays. But if you were to look along the optic axis for a calcite crystal, a quartz crystal, then the extraordinary rays would have traveled slower than the ordinary rays. That would have been the only difference. So the optic axis is coming out perpendicularly from the point P, so, and this is the refracting edge. So as you can see, I mean, for a positive crystal, I have drawn this thing. This discussion that I have held is for a negative crystal. In the case of a negative crystal, the ellipse will envelop the circle. In the case of a positive crystal, the circle will envelop the ellipse. So this is the optic axis, and the circle will be moving out and enveloping the ellipse within it. So symmetric about the optic axis in both cases. Let us now, in the little time that we have, because I have to leave at in 5 minutes or so, I will just start discussing the mathematical aspect, because after all, polarization.
Can we take two more questions because
Yes,
there
yes,
were
yes,
two?
yes. Fine, fine, fine. Then we can actually round it off at this page. The next few minutes we will stop at page 22, and we can take the two questions that have been raised. Yeah, yeah, that is fine. Hello.
Okay, just a second. Just a second. Let me. So there is a question. There is one question which asks: is there any wave exists which whose velocity is greater than the velocity of light?
Not in optics, of course, but actually, you can have such waves. In quantum mechanics, it is possible, relativistically speaking. See, every wave has got a. Well, actually, in optics also, it is possible, now that you mention it. Can you have waves that can travel faster than the speed of light, right? You're asking, right? Yeah,
Yes, that's
yes, yes, yes. In fact, there was this experiment carried out by some Dutch group. I remember having read about it, where this see, you can slow down the speed of light in a medium, right? As compared to, of course, this will not be possible in vacuum, but in a medium, the speed of light could be slowed down. So, in a particular medium, if you slow down the speed of light, and then after that you can make a particle travel faster than the speed of light in that medium, and this thing is connected to a phenomenon known as where particles can travel faster than the speed of light in a particular medium, let us say an electron. Incidentally, quantum mechanically speaking, the electron can also be a wave because it is wave particle duality. So, that sort of a situation can give you what is known as Cherenkov waves, a Cherenkov radiation, Cherenkov cone. Like in the case of sound, you have objects that can travel faster than sound, like let us say a supersonic fighter plane. So the plane will go past you and you will not hear anything. It's only after it has gone past you, you'll hear the sonic boom, and the sonic boom has got a conical wavefront. So particles that can travel faster than can be made to travel faster than light by slowing down the speed of light in a medium will show a similar phenomenon. This is known as a Cherenkov cone and a Cherenkov wave. I mean Cherenkov radiation. I'm sorry. So that is possible. But when you ask whether it is possible for a wave to travel faster than the speed of light, in quantum mechanics, when particles can travel very close to the speed of light, right? See, particles can be both waves and particles. Just like I said, light, which was supposed to be a wave, can be seen as both a wave and a particle. Einstein made light a particle. Similarly, material of particles like an electron can be seen as a wave. This was the doing of Louis de Broglie. Matter waves, lambda is equal to h by p, or lambda is equal to h by m into v. So particles can behave like waves, so electrons can behave like waves. And if you have some such subatomic particle moving close to the particle itself is moving close to the speed of light, then the particle can also be viewed as a wave. And the wave has got two kinds of velocities associated with it. One is a phase velocity and the other is a group velocity. Phase velocity of such particles can exceed the speed of light, but the group velocity does not exceed the speed of light. The group velocity is exactly equal to the particle velocity. So if you are asking for a wave that can exceed the speed of light, well, there is the example of matter waves of particles. Remember, matter waves of particles, what do I mean by that? Particles can be viewed as waves, according to Louis de Broglie. So such a such a particle can be viewed as a matter wave, and the phase velocity of that matter wave can exceed the speed of light. However, the group velocity cannot exceed the speed of light. So that will. So is that the first question you had, right? There was a second question.
Uh, so I mean, there is a follow-up question. Probably when you say matter waves, the question which is the second question followed by the previous one, which is I mean from the same participant, which is the de Broglie's wave whose velocity is greater than the velocity of
Yes. De Broglie waves can have phase velocities only for not for ordinary terrestrial or normal velocities that we experience. If you can make a particle travel very close to the speed of light, of course in vacuum no particle can exceed the speed can exceed the velocity of light, but they can get close. In some that sort of a situation, phase velocity can exceed the speed of light, but therefore it is always better to stick to group velocity. Group velocities are safer to work with, right?
okay.
Okay.
Okay. There is another question from another
Yes,
participant,
yes,
which
yes.
is how does the birefringence arise in the optical fiber? What acts as filter for light oscillations in optical fiber case?
Optical fiber, optical, what was, how does birefringence have, see, optical fiber, of course, makes use of total internal reflection. That I know. But is optical fiber material made of these things? I'm not very sure. That I'll have to look at. But what was the question again?
The second question, second question was what acts as filter for light oscillations in optical fiber?
What acts as filter for light oscillations as optical fiber? I'm not
In optical fiber.
in an optical fiber filter, but I don't know why would you want to filter? Because you'd want to make light pass through an optical fiber, isn't it? I mean, the core, the inside of an optical fiber is made of a material which enables total internal reflection. That I know. I'll just have to look it up. Maybe two questions can be kept pending: this question and the Maxwell boundary question. Is that will that be all right?
Yeah, sure.
So tomorrow we are to meet at 2. Maybe I should be able to come up with some answers to these two questions. Okay.
Yes.
Okay. So perhaps I can end here now because at 4:30 I've got to go for a meeting. Is that all right, Professor Rajendra?
Yes, probably if you can summarize I mean, the subtopics which you have covered, so that
Yeah,
I mean,
today's topic is just we just discussed basic features of polarization, that it's a wave phenomenon and it must refer to the electromagnetic behavior of light and transverse wave. Um, we referred to Malus law and Brewster's law, and then Brewster's law is dependent on polarization by reflection, and then we referred to polarization by refraction, Arago's experimental arrangement, and that principle was extended to the feature of double refraction in the case in polarization. So whereby we have extraordinary rays and ordinary rays, and extraordinary rays behave extraordinarily, and the phenomenon of double refraction is visible or can be observed when we use materials like calcite and quartz. And particularly with respect to calcite, there is this device known as the Nicol prism, which clearly separates the E rays and the O rays. And thereafter, we talked about positive and negative crystals and certain features of these polarizing material, like uniaxial behavior and anisotropic behavior, all of these things. And then finally, when we talked about the wavefront approach, wavefront picture, we talked about three cases of these things. refraction with negative crystals. We refer to negative crystals so that the E rays travel faster than O rays. So that's the brief summary of today's class. Basic theory of polarization. Hopefully, in the next 3 classes, we should be able to touch on some useful applications or some advanced features using these ideas. Is that all right, Professor Rajendra? Hello?
Yes, yes. So we can end the session today.
Yes,
Thank
yes,
you
yes.
very much for
Thank
the
you.
talks, and
Thank you.
we'll
Thank you.
continue with the rest of the topics in polarization optics tomorrow
At
at 3 p.m.
2 p.m. Right, right, right. Okay. Thank you very much. Thank you all.
Okay.
Thank you all.
Thank you.
Thank you all.